Welcome coders to my game engine series and this video about skeletal animation. To animate our character model, we need to rig the model and add animations to it, load it as glTF file, add two new fields to our vertex struct to bind each vertex to up to 4 joints from a skeleton, provide a vertex shader that supports vertex skinning, provide a buffer to that shader with transforms that are applied to each vertex of the model, and update the transforms each frame on the CPU by interpolating keyframes. We will show you how to find a suitable character model. Mixamo is very picky about models it can work with. You need to understand exactly what criteria a good model has. You don't need to rig a model yourself, you can have it auto-rigged. We'll show you how that is done. When downloading the animations, the first animation is downloaded with a skin, aka mesh. All other animations are downloaded without a skin. Use the in-place option whenever you can. Then we'll show you in Blender how to make all those animations in place that do not have the option in Mixamo. Also in Blender, we will then apply all the animations to a single armature, aka skeleton. If you like to skip all previous steps, there's a ready-to-use Cesium model under Application, Lucre, Models, External 3D Files, which contains 5 animations. Then in the engine, we'll show you how to load the resulting glTF file with the header-only library tinygltf. We'll take a look at the new Vertex shader. We will explain where the keyframes come from and how to interpolate between them. Then we will show how to recalculate the matrices in the buffer for the Vertex shader. These matrices are applied to each vertex of the mesh and cause the actual deformation. And then we will show you a class to manage multiple animations. By the way, I'm JC, your host. This video also got contributions and support from Mantar from Discord. So thank you very much, Mantar, for all your help. I would like to clarify some terms to avoid any confusion. Armature and skeleton mean the same thing. Normally, an armature refers to the windings of an electrical motor. The term is also used by artists for the support structure of a hollow model. We use it in a similar way. A skeleton is comprised of bones, and bones are connected via joints. The joints define the transform, so we will only use the term joint. For us, a skeleton is made up of joints, not bones. A skeleton in software can be represented as a tree hierarchy. A joint has one parent and can have multiple children. The hip is the root of the skeleton and has no parent. The term rigging means to add a skeleton with bones and joints connecting the bones to the model. The bones and joints define how the model deforms. This is also referred to as vertex skinning. If you want Mixamo to auto-rig your model, it has to be in a perfect T-pose. It has to be a clean mesh with a single surface with no holes, symmetrical, centered in the scene, facing forward, with the feet touching the origin and with distinguishable features. It won't work if there are accessories like glasses or a weapon. And here's how not to do it. I tried to use the monkey model you may have noticed in the background of my scenes. This is a bad model. It disintegrates into 1,000 pieces when the animation is applied. One last tip before we go into Mixamo and upload our model as FBX file. Do normalize the scale of the model and make sure in your engine it looks good when all scale values are set to 1. When the model is rigged and animations are applied, it's hard to normalize the scale of the model. Then in the scene collection of Blender, delete anything unnecessary and rename the fields to your liking, then export the model as FBX. Now we are in Mixamo and ready to rig our model. This is super easy. All we have to do is drag those circles to the right spots. The auto rigger will do the rest for you. Now we can download animations. The first animation we download with a skin, all others without. Pay close attention to the in-place option of an animation. If an animation has it, be sure to check that option. If not, I'll show you in a second how to fix that. Back in Blender, we import the first file with the skin. We rename the animation and delete everything we don't need. Then we need to fix the material. So we go to the first model and the UV editor. We go back to object mode, select the new model and delete its material, add a new one, and the texture from the original model. And back in object mode, the material is fixed. Now we can remove the original model. Then we go to the NLA editor and push the animation down. Now we can load the start walk animation. This one is not in place, so we need to fix that. We rename the animation. We go to the graph editor. We select the hips and the Z location. With Ctrl H we can hide all other graphs. With View, Frame All, we can scale this graph, and with Key, Snap, Selection to Cursor Value, we make it in place. Then we go to the NLA editor, push it down, and delete the animation. Blender has saved it now. Then we add a track, we add an action strip, and here we need to add a blend factor. On the timeline, we adjust the last frame. Then we check if the animation works. This looks good. Now we repeat the steps for all other animations, export the file to glTF, and we're done. The first thing we do in our engine is to load the glTF file and inspect it. I'm using tinygltf as a loader, and I'm putting a breakpoint right after the load function. The glTF loader provides a structure to us that is populated with the values it retrieved from the model. In the field Animations, we see 5 animations: idle, jumping, start walk, stop walk, and walk. Each animation has a field for samplers and channels. Further down in the glTF model structure, we find the field Skins. It must have only one element. Here we have inverse bind matrices that points to accessor 6 and an array of joints. Each array element points to a glTF node. The first element points to the root node, node 66 in this case. Let's check the nodes field of the glTF structure about node 66. It says Mixamo rig hips. This is exactly what we expected. Down here, it gets interesting. We have a field children with 3 elements. The values here point to child glTF nodes. So starting with this root node, we can get a hold of the skeleton. What's also noteworthy are the 4 fields below children: rotation, scale, translation, and matrix. We are only interested in the matrix field, as the other 3 fields will actually be provided by the animation. If the matrix field is empty, we have to use an identity matrix. Now, let's load the data we found so far. To load the skeleton, we need 2 structs, joint and skeleton. The skeleton struct has a vector of joints. This vector corresponds to the array we saw before in the glTF model structure under skins. Then it has a map that maps from glTF node indices to elements in this joint vector here. Before, in the glTF model structure under skins, we saw the array that maps from joints to glTF nodes. This map here does the opposite. For a given glTF node, it provides a joint index. We need this map when we recursively traverse the tree hierarchy of the glTF nodes. Then it has an update function that we will call each frame. And it has an update joint function that can be used to recursively update the tree hierarchy of our skeleton. The joint struct has a parent joint index that refers to the joint vector of the skeleton. It has also a vector of child joint indices. Then up here, it has an index for a glTF node. That was the 66 for the root joint that we saw before. It has a name, it has an undeformed node matrix, which corresponds to the matrix field we saw in the glTF model structure before. Here we have an inverse bind matrix that we will get from the glTF accessor 6. Then we have a vec3 for translation, a quaternion for rotation, and a vec3 for scale. These three fields will be written by the animation. Then the joint struct has the function getDeformedBindMatrix, where the output of the animation is applied. It multiplies the undeformed bind matrix with the scale, rotation, and translation. We will load the skeleton in two steps. In the first step, we will just do a for loop over the joints array of the skins field in the glTF model structure. For each joint, we will grab as much data as we can, but we will leave the parent joint and child index fields out. In this step, we also set up the map to translate from glTF node indices to joint indices. In the second step, we will use a recursive function loadJoint that is called with a glTF node index and a parent joint index. It fills in the parent node and calls itself recursively for each child of the glTF node. Up here, you can see another struct called shader data. It holds a vector of mat4s for the final joint matrices. This vector will be updated each frame on the CPU side and then copied into a UBO on the GPU side. In model.h, I created a template to load glTF accessors. A glTF accessor is a descriptor for a generic data buffer. An accessor has a count, a type, and a component type. Type could, for example, be a float, a vec3, or a mat4. Component type is float for a vec3 or a mat4. The function returns a pointer to the data buffer. In modelsa.cpp, you can find the implementation of the skeleton load function. Here, we get the number of skeletons, create an animations vector, and the skeleton struct. Then we get a reference to element 0 from the skins field of the glTF model structure and create a reference of the destination joints vector in our skeleton structure. We retrieve the number of joints and resize the joints field and the buffer for the shader data. Here we have a mat4 pointer called inverse bind matrices that we pass to the load accessor function along with the accessor index inverse bind matrices from the glTF skins field. This was the value 6 that we saw before. Then comes step 1 of setting up our joints vector, where we loop over the joints array of the glTF model. In the second step, we set up the root node, element 0 of the glTF joints array, and call the recursive loadJoint function. Down here, we also create the UBO for the shader that holds for each joint a mat4. the load joint function sets up the parent joint, which is an index to an element in our joints vector. It retrieves the number of child joints from the glTF node, resizes the vector of child indices, and then for each child it retrieves an index into our joints vector via the translation map, and then calls itself recursively. Now we have the skeleton loaded. I hooked up the 5 animations to the gamepad input. You can use the left analog stick to walk around and the X button to jump. It starts to feel like a real game. Back to loading the glTF file, we need to add 2 more fields to our Vertex struct, an integer vec4 called joint IDs and a regular vec4 called weights. The joint IDs are used to index into the UBO we created earlier to retrieve a transform. The corresponding weight defines how strong that transform influences a vertex. The glTF format allows for up to 4 joints to be bound to a vertex. Here in model.cpp, in the code to load vertices, we check if the glTF model has joint IDs and weights and use the load accessor function again to set up pointers to the corresponding buffers. Down here, where the vertices are created, we assign the joint IDs and weights. Be sure to check in your code the component type of the joint IDs. I've seen them as 8-bit integers and 16-bit integers in different glTF models. Lastly, in the Vulkan code in vkmodel.cpp, we push 2 new attribute descriptions into the vertex input attribute description vector. For the 4 joint IDs, we use RGBA sint, and for the 4 weights, we use RGBA sfloat. In the vertex shader, we add 2 new input fields for the integer vec4 joints ID and the regular vec4 weights. Up here, I use an include file to define the maximum number of joints per model and the maximum number of joints per vertex. Here is the new UBO that holds the joint matrices. In the main function, we calculate an animated position and a combined joint transform. By looping over all 4 joints, a vertex can be bound to. If the weight is 0, we can skip a loop. If the joint ID of a vertex is out of range, we give the animated position and the joint transform default values. Here, we calculate a local position by applying one of the 4 joint transforms to the regular position field of the vertex. Then we add this value, according to the influence weight, to the animated position. We also add the joint matrix according to its weight to the joint transform. Then down here, we calculate the world position as usual, only now we use the animated position. To calculate the normal matrix, we transpose the inverse of the original normal matrix times the joint transform. Frac normal and frac tangent are calculated as before. Keyframes define model poses at different points in time during the animation. Between 2 keyframes, an interpolation is applied. The glTF file format offers 3 interpolation methods: linear, step, and cubic spline. For the vec3s of the scale and translation, the linear interpolation blends the vector components linearly over from one keyframe to the next. We can use a regular lerp function. For the quaternion of the rotation, we have to do a spherical interpolation, which is also referred to as slurp. The step interpolation is easy. It sets the values to the nearest keyframe. The cubic spline interpolation I did not implement. While I'm a huge fan of splines, I doubt you could tell the linear and cubic spline interpolation apart at 30 animation updates per second. Here are some terms the glTF file format defines to deal with animations. An animation path can either be scale, rotation, or translation. An animation channel is applied to one joint animates either the scale, rotation, or translation, so it animates one animation path, and its keyframes come from an animation sampler. An animation sampler has a set of keyframes, whereby each keyframe has a timestamp and either a vec3 for a scale or translation, or a vec4 for the quaternion of a rotation. Let's take a look at the code. Here we have the header file for skeletal animation. There are type definitions for an animation path, an interpolation method, an animation channel, and an animation sampler. The sampler is holding keyframes. It has a vector of floats for timestamps, and it has a vector of GLM vec4s that can be used for both quaternions, which have 4 components, and the scale and translation, which have 3 components. The animation sampler also has an interpolation method. A sampler is used to animate either the scale, rotation, or translation of a single joint. The animation channel has a path, an index for an animation sampler, and a reference to a joint. Then the animation has a range of public functions to start and stop it, check if it is running, check if it will expire in the next frame, get its name, set repeat, update the skeleton, get its overall duration, and get its current time. Then it has a vector for samplers and a vector for channels that we need to load from the glTF file. Down here it has variables for a name, a flag to restart, and the time for the first and last keyframe, as well as a time for the current keyframe. Let me show you quickly how to load animations from a glTF file. I skipped this part earlier to introduce the topic first. So we get the number of animations from the glTF model structure and loop over all animations. For each animation, we get a reference to the current animation from the glTF model, create a skeletal animation object, get the number of samplers and resize the samplers vector accordingly, loop over all samplers and copy the data over, set the first and the last keyframe, get the number of channels and resize the channels vector accordingly, loop over all channels and copy over their data as well. Then we push the animation into an animations vector. And lastly, we set a material flag so that the engine can select the right render system. To take a break from all the code, I can show you the debug GUI in Lucre and how you can select animations there. Use key M, as in Mike, to bring up the menu. The implementation of the skeletal animation class is easy. The most important function is update. It terminates right away if the animation is not running. Then it increments the current keyframe time by the time step provided in its arguments. If repeat is enabled, it will wrap around when the current keyframe time is larger than the last keyframe time. Then the update function loops over all channels. This will update either the scale, rotation, or translation field of a joint. So for each channel, it loops over the timestamps vector of its sampler. If the 2 keyframes are found that cover the current animation time, the interpolation is applied. After the animation updated all joints, we recalculate in the update function of the skeleton the final joint matrices that are used in the V shader. This happens in 3 steps. Step 1. For each joint, call getDeformedBindMatrix. This will apply the new values for scale, rotation, and translation to the undeformed matrix of a joint. Step 2. Traverse the skeleton starting with the root and calculate for each joint its global transform in bone space by multiplying the global transform in bone space of the parent with the deformed bind matrix from step 1. The recursive algorithm makes sure that for each joint, the global transform for the parent is already up to date. The function updateJoint performs this calculation and then calls itself recursively for each child joint. Step 3. Loop over all joints again and apply the inverse bind matrix. This will take the global transform from bone space back into model space. Now the joint matrices are good to go and can be sent to the V-shader. We can copy them into the UBO. The class Skeletal Animations handles multiple animations per model. It's a wrapper for a vector of animations and a map that translates from names to animations. This class is intended as a user interface and shall be used on the application side. It defines an iterator to traverse all animations with a range-based for loop and overloads the array operator so that it can be used as a map or an array. I don't want to dwell on this class too long, as you guys are more than capable to write your own animation manager. And this concludes this episode. Thank you for watching. Good luck with Skeletal Animation. If you have questions or feedback, please let me know in the comments. I would like to know what you guys are working on and what you would like to see next. By the way, you can find me on Brendan Galea's Discord server about game engine development. Needless to say, please like the video here on YouTube and subscribe. Please also like the engine on GitHub. See you next time. Bye bye.